Okay, welcome back Physics 30s to our next lesson. This is 6.3, and today we're going to be talking about the Bohr model.
So, Mr. Rutherford, what's your idea of what the atom looks like? Okay, so I did this experiment, right, where I got this alpha particle gun, and I took this gold and I smashed it super thin, and I put this thin gold foil and I shot these alpha particles at it. Now you'd think, right, that these alpha particles would just pass right on through the gold foil, right? That's what I thought. But then what we got was that it bounced off and actually came back. Super weird, right? So check this out. This is what I think. I think instead of being like this raisin bun, it all kind of spread out, all that mass is kind of sucked into the middle for this super dense nucleus, and the electrons, they're just going around the outside. Pretty cool, right? What do you think? Okay. What? No, it's good. You did really good work. What's wrong with it? Well, it's just your model has an orbiting electron, and if it's orbiting, it's in circular motion and technically accelerating. If we have an accelerating charge, it should be emitting EMR. Oh. And then it's going to be giving up energy and going closer and closer and closer and just smash into the nucleus. I guess so. And even if it did that, we should get a continuous spectrum, but we see that we only get certain spectral lines. Well, okay, so Rutherford didn't have the atom completely figured out, so we need to keep experimenting. So what to do next? Well, how about we take a whole bunch of atoms, put them into a glass tube, and just zap them with electricity. See what happens. So that experiment looks like this. We take this glass tube and we put electrodes on each side so we have a positive and negative charge, and we're going to send electrons through. However, this isn't going to be a whole bunch of gas. We're going to put a certain element in there, but we're going to suck most of it out. So there's only a couple atoms of this gas and they're really spread out. This is called a rarefied gas. And the result is that when we put electricity through it, we get this glowing light. You may have actually seen a light like this, as this is what's used to make neon signs. Now this isn't normal light. To look at it more closely, we're going to put it through a diffraction grating, which is going to split it up into its different wavelengths. And you'd expect maybe continuous spectrum from light, but instead, we only get these certain bright bands, which is kind of weird. So let's try it with another element, and we get different bright bands, but again, not a continuous spectrum, only specific wavelengths. Why is that? Well, we know from previous lessons that light comes in photons or packets of energy, and its energy is based off of its frequency in the formula E is equal to HF, or its wavelength, and E is equal to HC over lambda. And the results of our experiment are saying that this specific element can only emit certain energies or certain wavelengths, and that a different element can only emit other energies. So this gives us the idea that atoms can only have specific amounts of energy. Introducing the Bohr model by Niels Bohr. This model says that electrons are going to exist in what we're going to call for now as stationary states around the nucleus. And that we can have electrons in this shell at this energy level, and we can have them in this shell or this energy level, but nothing can be in between. It can have this much energy or this much energy, but nothing in between. And again, the big idea is that the electron can exist here or it can exist here. It can't be in between. It can go back and forth between these two places, but it actually spends no time in between. Now, how does that relate to the colors that we're coming off? Well, if we run a current at this atom, we're going to send electrons at it. The electron is going to absorb that energy and get excited. Woohoo! But the electron will then soon lose its energy, jump back down, and give its energy away as a photon. That photon of light that it emits is specific to the jump that the electron made. However much potential energy it lost by falling back down is the energy of the photon that's going to be emitted. If the electron gets more energy and jumps up into a higher state, when it falls back down from that state, it will give up more energy and give off a different color of higher energy. So now we know that those bright lines that we saw are matching those jumps or the gaps between that atom's specific orbitals. And there are a lot of dark regions because the electron can't jump up in between states, come back down, and emit a different wavelength. It just isn't allowed to make that jump. So here's our conclusions for the Bohr model. Electrons exist in quantized orbitals. An electron can be in one orbital or another, but it can never be in between. In their most stable state, electrons are in what we're going to call the ground state, and when they gain energy, they jump up to an excited state. After being excited, electrons soon are going to lose that energy and give it up as a photon. The photon that the electron gives up matches the energy change of those change in states, And this is what's going to give us a distinct, what we call bright line spectra, as we can see at the top of the page, that is specific for each individual atom based off of its shells. All right, so I hope that helped you to understand the Bohr model. Thank you so much for watching this video, and I will see you in the next lesson.